Hello everybody, my name is Dora and today I will be presenting the paper Fast and Efficient Bit-Level Precision Tuning, which is a joint work between Saleh J, me and Mathieu Martel from the University of Perpignan in France. To start with, developers without extensive background in numerical accuracy are likely to use the higher precision available on their machines. And while the results are more accurate and robust, but these results in a higher execution time and an increased memory and energy consumption. So the goal from this work is to find the best trade-off between the accuracy and the performance by using a reduced precision for the variables and by satisfying at the same time the user accuracy requirement. This process is called precision tuning. In the last years, much attention has been paid for the precision tuning problem, as you can see here in the following figure. In fact, we found dynamic tools such as Precision, Craft, HIFP Tuner, etc. Also, we found some static tools such as FP Tailor, the Daisy tool, the TAFE tool, and so forth. In fact, a common point of all these techniques is that they follow a try and fail approach, which means that they change the data types of some variables of the program and evaluate at each time the accuracy of the results. In this paper, we will present our tool POP, short for Precision Optimizer, which originality is based on a semantical modeling of the propagation of the errors through a numerical program. In fact, to understand the technique embodied in POP, we start by presenting some preliminary notations and definitions. So, the first definition is the UFP of a number x. In fact, the UFP denotes the unit in the first place of x, and it is given by the following equation. The second definition is the NSB of a number x. Intuitively, the NSB denotes the number of significant bits of x, and formally, if we assume that epsilon of x is the absolute error between x hat, which is given infinite precision, and the value of x, then the absolute error can be bounded as shown in this equation. Finally, we present the unit in the last place, which is the ULP of the number, and is computed by the UFP of x minus NSB of x plus 1. Concerning the error, so the error is introduced by the finite precision computations and by assuming that the constants occurring in the source program or the source codes of POP are exact. Consequently, we define in the same manner the UFP of the error UFPE, the NSB of the error NSBE, and the ULP of the error ULPE. We move now to present the main architecture of POP. In fact, this architecture incorporates three major steps. The first step, POP takes a program annotated with the user accuracy requirement, then it parses the program and generates the equivalent syntactic tree. After, POP performs a range analysis on the program variable values. Let us take an example. Here we have an example of the pendulum program, which models the movement of a pendulum without damping. This program, as you can see, contains several annotations, loops, assignments, conditionals, the sign function, etc. And on line 14, we found the require NSB, which is a statement that informs POP that the user wants an NSB equal to 20 bits on variable y2. Then, POP attributes a unique label at each control point of the program. Now, we attain or we reach the second step of analysis of POP. In fact, POP is based on a static technique relying on a semantical modeling of the propagation of numerical errors. More specifically, POP generates an integer linear programming problem ILP from the program source code And basically, this is done by reasoning on the UFP of the values which are known at the constant generation time and the NSV of the values which are unknown. After, this problem will be solved using a classical linear programming solver such as the GLPK solver. So at this stage, we need to say that in this ILP formulation, we were pessimistic on the propagation of the carry bit functions. This over-approximation is expressed by the function xi is equal to 1. So, if we take again the pendulum program, and if we focus on line 6 of this program, here we have an assignment, an addition, and a multiplication. Then pop for this line generates 7 constraints. The first one are for the addition, followed by 2 constraints for the multiplication, 1 constraint for the assignment, and the 2 last constraints are for the over-approximation carry bit function for the addition and the multiplication respectively. We need to mention that pop generates such constraints for all the statements of the program. For now, pop handles loops, conditionals, program with the 4 elementary expressions or elementary functions, the trigonometric functions, etc. And in terms of complexity, the number of constraints and variables are linear in the size of the program analyzed. As a result, after solving these these constraints, pop succeeded in tuning the majority of the program variables, and the 20 bits that were required on the variable y2 were correctly propagated from the results and into the inputs of the program, giving a total of 861 bits at bit level against more than 2,300 bits for the original pendulum program, in which all the variables were in double precision. The question now is how we can optimize more the precisions by being less pessimistic on the carry's propagation. And this is the subject of the third step of our analysis. In fact, we have observed that when we analyze larger codes with pop, adding 1 bit at each time becomes costly. For this reason, we will propose a new formulation of this function. So, let C1 and C2 two constants of some of the addition operation, whose result is stored in the variable x. Then, if the ELP of the error of one of these operands is greater than the UFP of the error of the other operand, then in this case the two errors cannot overlap, and adding 1 bit in this case is useless. This new xi function can be mathematically formalized by this equation, in which we have a new min-max operator that appear, and consequently the program or the problem is no longer an ILP. For this reason, we have used the policy iteration algorithm, which is usually solved to solve the nonlinear fixed point equations. So to be brief, if we take the example of or the constraint of the xi function, the principle of our algorithm is to choose a policy, initial policy pi 0 by bringing the min and the max of this formula. After, we will associate the function f to this policy, and what remains to be done is to solve the corresponding ILP problem. So, if a fixed point is reached, then the algorithm terminates. Otherwise, pop iterates with a new policy. And we need to know that the number of policies is limited or is bounded by the number of iterations. So, by using the policy iteration method, and by taking again the line 6 of the pendulum program under discussion, then pop generates a new or a finer set of constraints C2, which will be added to the former set C1, in which the only difference is we activate this new carry bit function instead of its over approximation. Thus, we found that the tuned program using the policy iteration technique, uses less number of bits. Especially here we have measured in orange the gain of bits that we obtain on some variables, giving a total of 843 bits with the policy iteration method against 861 that we have found by using the pure ILP. So moving to evaluate the performance of POP on some examples. So here, as you can see in the table, we found that the optimization in bit level by using the policy iteration technique is more important than the optimization with the ILP formulation. Also, what we can see here is that in terms of speed, so by both techniques, POP found the new results or the new precisions in really few seconds. Also, if we stress on the negative percentages that we can find here in the green or mentioned in the green color, we can say that POP returns new formats for any threshold required by the user without any cost, nor by increasing the complexity of the analysis, even it fails to have a significant improvement on the program output. And also, if you want to translate the bit level or the number of bits obtained in the IEEE 754 formats, we only need to approximate to the upper number of bits that corresponds to an IEEE 754 format. We finish by some comparison between POP in its new version ILP and POP in its former version using the SMT solver Z3 and the prior state-of-the-art parsimonious. Here we took benchmarks from both tools, which mean parsimonious and POP. And we found that POP saves more bits for the majority of the programs that we have tested and for the different error thresholds asserted. And the POP finds the new precisions in really few seconds if we compare it to POP SMT or even to parsimonious. Also, we need to say that parsimonious saves more bits only for one example, which is the relation example, whereas POP remains fast for this example. So, to sum up, we have presented in this article new approach for precision tuning with two kinds of methods. First one is a pure ILP with an over-approximation of the carry bit function, and the second one is the policy iteration technique for more precise carry bit functions. So many research directions are possible. First one is to use a commercial solver such as Cplex in order to have or to solve more important ILP problems. Also, we can reduce the number of variables by assigning the same precision to a whole piece of code, such as the same expression or the same loop or conditional, etc. We aim to combine POP with other tools of code transformation or error analysis. And in long term, our technique is also adaptable for GNNs and for synthesizing codes for the fixed point arithmetic. So at the end, we present the main references of POP in its former version and in its new version. And we thank you all for your attention.